Hi, I'm Andrea, and this is Astra. Okay. And outline our presentation. Overview of our team members, and a breakdown of our organization. And some of the acronyms you'll be seeing in this presentation. All right, for the overview, our mission summary, deployment at 670 meters. During descent, we will determine optimal separation prior to 400 meters. Stable video recording that needs no location, and also successful recovery of the secondary objectives include receiving every 5 seconds and autonomous control of the reset function. Our selectable objectives are those one that shows the ability to use an accelerometer to measure the stability and angulate distance. This is a summary of the major system requirements, including CanSat weighted at 600 grams, also loaded 10 container that is using a zero envelope. After the assembly of the container, helicopter recovery system with science vehicles, as I said before, the video camera with orientation mode. Telemetry, aircraft, and also to the telemetry display the field time and action. This is a concept of mission operations on the ground to show the plans, launch, deployment, separation, and disengagement. This is an example of the physical layout we decided to go with. You can see there's a container
So these are two cameras that we use payload. The two major structural elements of the payload are the aluminum standoffs and plates. The payload's split into three sections. The camera at the bottom, the electrical system, and flip flop. The serial at the top of the container. These are just some requirements for this container has to be passive. Also in the requirements, just the structural integrity. So here we have mechanical data. Based on those also there's no sensors are exposure. And also so this is just some more possibilities to use. So this shows how we can separate the container payload once we decide that we can the payload there for that model itself, but then we put into place so we haven't conducted any tests of the effectively we want to have a lot of testing develop full model, adaptive model, before that so
So we don't have a set in stone map, but that we have much measures. So what delegated between subsystems to develop a budget that we are going to try to operate so the breakdown will have our container will be about 15% of our mass. Five people, about 40%. Sensors, because they have most electrical components, will be about 20%. FSW, since it's mostly just wires and making sure all things are communicating, maybe about 5%. CDs and GPS, 10%. That's a little more. Battery, GPS, all the more hardware, we'll have an extra 5%. So for the max budget for the payload, one thing I forgot to mention is that the interconnection budget, although it is like part of the main payload, it's going to go into the max payload. The only thing that isn't included in that is the so here is the payload and then in case under weight, for over, we'll drill holes in the plates in CanSat. And then for some reason we're under mass, we'll have 500 plates to attach to it. So thanks to work for the management subsystem. Our main priority right now is to perform structural engineering. Mainly the integration of license and the actual structural we need to sign up material for the actual container outside of the container for the design station. And then basically start programming First, there's some basic atmospheric conditions like pressure and temperature. Usually, we have testing altitude. We're also monitoring stuff that we use parameters for sensibility and trajectory direction and that includes anything like acceleration, rotation, or even compass heading. And then we have both voltage sensing as well as electrical. We also have a video camera that's taking so that's kind of just a big overview of how this is laid out. We have a 100 sensor video camera, and we have this really awesome animated for our sensors. So on there we have pressure, temperature sensor, so on there and magnetometer. We just use that on we're using that to estimate altitude, and that's just for this is our annual temperature sensor. It's really small. We also have an IMU, which is very good at accelerometer gyroscope and the key with why we're adding multiple gyroscopes and the competition to determine the orientation of these types of things. And then also the trajectory pulling it or whether it's stable. Our binoculars objective is to record accelerometer data and store it on the SD with the video camera, we have another trouble with the first one that worked, but the only took still images and not having a lot of trouble with video feed. So we ended up using this one, which is more comparable to the GoPro. We have HD video, and you can also save video files on this one. Another key that we're using a completely separate battery for the power and that also stays inside the camera. The last thing I want to mention is what one we're using to locate the CanSat. So it's called an audio computer. It's just a speaker. Some of our current progress, we've purchased all the sensors and we've been able to collect data everyone individually. And right now we're working on a prototype to actually put them all together and do it. And working kind of so far, we really just need to work on as I said, I think we need to start working with new video all the sensors. Okay, so this is the main thing we've been working on. That's the NDR. So we have to figure out what states we want, and this is one of the competition requirements. And we'll go throughout the entire site and move from state to state. So about organize our code and figure out what is doing what, and then we'll move on. And one thing before we get to that, for example, software called storage. There are three key things that need to be stored. Video camera footage, which will currently be on the permanency card. And also stability and able to send design vehicles that are selectable on any future detectors, and this will be stored on the SD card. And like software, stored on the same SD card and the it didn't have like software stay on there because in case there's a momentary loss of power or something gets messed up, the Arduino gets funky for a second, it can read its state from the SD card, and it'll be able to continue going from where it left off. You wouldn't want something to go wrong and have to go all the way back to the pre-flight testing. Now, when we first put the CanSat inside of the rocket, it's going to go through a pre-flight test. It'll turn on all of the sensors in the video camera, it will see what transmits, and we'll make sure everything's working. It should be pretty quick and will draw a lot of power, but it will be for a short time. Then it will be the launch wait, and that's when it's sitting on the, just sitting in the rocket waiting to shoot up. We're going to only keep the Arduino and accelerometer on. It'll move here directly after the pre-flight test, and then we'll wait to detect the acceleration to move on to the next stage. We then have the ascent state, which is when the rocket's flying through the air. All the sensors in the video camera will be turned on, even though the video camera will just be recording the rocket. This is one of the rules. The video camera has to be recording from
lift off until it lands. For stabilization, so when the rocket reaches apogee, and the accelerometer detects downward acceleration again, all sensors and video camera will remain on, and the parachute will automatically release. It is stuffed on top, and then when it's released from the rocket, it will naturally come up. This will be medium power drop, and this will be the science vehicle falling inside the container. And then we go to the separation stage. We move to this when the CanSat is deemed stable, and in competition we'll stay before 300 meters, but we need some leeway, and in a perfect world it'd be more like 400 or 500 meters, but in the end we'll probably have to for sure go before 350 meters to be safe. Everything will remain on, and we'll have to rotate the servo motor to release the science vehicle from the container. This will be a very high power draw, but very quick. Then the descent stage is when the science vehicle needs to fall into the passive auto gyro system, and then move to this mode after it's separated. All sensors and camera will remain on, everything will be stored to the SD card and transmitted, and then it'll be a high power draw without once it lands, it's been on the ground for about 300 seconds, a little bit. It'll turn on the noise beeper or the audio beacon, and then this will be a pretty low power consumption, and this will last for a couple hours, so we have time to find it. We have to do two main trade studies. Just basically find a micro SD reader, and then find a micro SD card that works well with our Arduino. This is just some of the sensors we use, making sure they will all connect to our Arduino. And then future work. The main thing we need to work on is implementing these states that we figured out, making sure they all work, and then just testing the code of the actual hardware all in all. And then next is range control with communication data.
So this is an overview of communication data handling. The major components are the two XP Pro Series 1 radios. We're also using the USB Explorer to connect the XP on the ground to the ground control laptop. And we'll be using the Arduino Nano microcontroller to use this video. So the overview requirements of this group. Main one is like one that's here. Here's the trade study we did for the microcontroller where we supposed to be able to do it. And we chose this one because it has it fits all the requirements of the mechanical process use. And it has 14 different pins that operate 5 volts, and it can provide AC 40 milliamps. And it has 2 serial input outputs to receive and transmit TCL serial. And if you take 6 to 20 volts unregulated or 5 volts regulated. Here's the case study we did for the XP, where we sold for the XP Pro. And in terms of antenna, we chose to use an integrated on board the CanSat. And on the ground station, it'll use an RPS and a connector with a larger antenna. Okay, so one of the requirements is to have a real-time clock, and we'll be doing this through our software. Programming language supports the millis function, which returns the number of milliseconds before passage before the switch turns on, and this is how we'll be tracking this again. So the radio configuration, as per competition guidelines, the 10ID/NID will be our assigned machine number, 5676, and it will be on channel C. The specific requirements for 2 FPs are trained again, autonomous initialization of the lens data. This will happen automatically when flight software reaches state 4 stabilization. We begin sending data, and then we're going to terminate telemetry when altitude is constant for 3 minutes, and we throw the threshold due, and when the threshold is granted, on display will go. So some basics for telemetry. This is the data that we have to send. That Mark talked about earlier. All data will be transmitted at 1 Hz rate. So we're sending 1 data packet per second. And of course, using a burst method, we'll be sending data continuously. So this is a current format that we're working with for data packets. So it's basically just going to be a string. Each different data being separated by a comma. MATLAB can immediately convert this string into separate vectors based on where the commas are placed. So future work, we need to integrate the FEs with the sensors and flight software, and we test the FE. So next up is the power subsystem. So in an overview, we have our main power supply from the 9-volt battery, which leads to voltage regulation unit, which in our case is just the Arduino Nano microcontroller, and three main things, categories that will be powering the separation and stabilization mechanisms, sensor protection units, and communication wireless mechanisms.
So this is just over to the requirements again. We have to take up the question of the one in regards to the battery
Here's a schematic block diagram that we're working on right now. So you can see the two power rails and 5-volt to 3.3 volts and signal wires along with the serial protocol that communication protocol that we use. So again, batteries will be supplying the power to the Arduino, and the Arduino regulates the voltage. All electrons will be inside the science vehicle, as Mike mentioned earlier, and we will have an external switch that powers the verified. So here's our current project. You can see this is our flat sat, our breadboard prototype we're working on. So once we finish this breadboard, we're going to begin working on with Altium to develop a PCB and again using printed circuit board that's going to save space inside the science vehicle and significantly reduce the mass of the system.
So here's the battery case study that we did. You guys are going to 9-volt battery that we want to run it. Pay special attention to the requirements. This battery fits under everything as a lithium-ion battery.
So here's the power budget, and this will show in milliwatts the power that each individual electric component will need. And here you can see the energy, and basically the total power required here is 253 milliamp hours, and there's a 10% insulation built in. And the battery that we chose at a 500 milliamp discharge will have 430 milliamp hours of power, which is more than discharge of the 500 milliamp
For the battery voltage working, we'll be using an Arduino and built in ABC with it as a regulated 10 bits. And there's just an example calculation using the numbers of the Arduino Nano. We get a resolution of 4.88.
More with the work here is that we need to work with mechanical subsystems to create the power to and we need to keep our circuits modified and good.
There we can see that.
CC overview, ground control, establishing communications with CanSat, and announcing the design, and plotting the run through in real time. This is the overview of those requirements. This being a great study, we went ahead and decided to go with the Yagi, but the antenna game as well, mostly because the lab already had it, and took those are requirements. And this is just a kind of an estimation of antenna beam ranges, and the antenna we chose fits our requirements and is more than enough for my calculated distance prediction the max distance of 860 meters. The Yagi will be well within that. This is just a mock-up of the ground station. Thinking about mounting the antenna via tripod and maybe a tripod to and paperwork, mounting tripod or build mount for the antenna, connecting the antenna radios to the computer, and utilizing that map to deploy the units.
Okay, so CanSat integration testing is obviously done actually for top so the levels of integration here is coaching the telemetry unit and basically flight software, CDH, sensors, and ground control going to work together to successfully send one data back and forth. Physical integrity unit is mapping the sensor control. We need to work to develop physical solutions the challenges presented, and electrical integration is electrical subsystems working with every other subsystem in power. Here's the sequence of testing. First start out with sensors, finding our sensors and ensuring that they work, and move down to communication, which is fixing the XPs and making sure the XPs communicate. So we've already completed these two steps. The next step here is flight software, which is again integrating code with all the sensors. Then we move on to electrical, so making sure that we can power all the components without USB, so we can take our testing in that level. And then once we complete the mechanical design, we can begin testing in the competition environment, which is outside of higher altitude. And cassette control, once we get the separation mechanism and stabilization working, we'll be able to drop it from the altitudes that are required in the test. And the ground control is the final step, and this is just making sure that MATLAB can plot all the codes correctly. So these are some quick overview of all the testing we need to do. A lot of this has already been talked about. Again, the major one is making sure that flight software sensors and CVAs and successfully communicate with each other and send traffic together. And EPS, we need to test battery voltages and ensure that the battery length, that the battery will last the duration of the flight. Mechanical needs to do some dropping prototypes from 700 meters. And cassette control needs to verify that the parachute will work with the stabilization and the rotor link. Finally, the ground control station needs to test the I'm going to hand it over to Mark, who's going to talk about mission operations and launch.
And so it's sort of a long ways away, but this is kind of just proving that we've talked about what we're going to do once we get to the competition. So once we arrive at the launch site, we're going to have a bunch of pre-flight checks on both the electrical and mechanical systems. And we're going to have to put everything into the rocket, obviously, that NASA developed. Spencer already talked about the different flight software suites, so obviously we'll be monitoring the launch deployment from the rocket itself, and then when the science vehicle separates from the container, which is already released its parachute, and then of course the science vehicle landing. Recovering the CanSat may be kind of a challenge, but we have a couple different things in place to do that, and eventually download all the different information from the SD cards and the camera. After that, we have to analyze all the data and do the presentation. We have a couple ideas for actually locating, covering the CanSat. In terms of the science vehicle, we're right now considering writing some sort of software that'll be able to track the trajectory of the CanSat throughout its flight. So we'd use all the IMU data as well as the altitude data, and we'd probably also have to take into account wind speed on the day of the flight. Then, of course, we have the speed around the CanSat.
This is our current schedule. Our PDR here today is early next month for the Air NASA PDR. Meanwhile, we're going to be continuing designing, building, and testing, keeping in mind our future deadlines. I proposed hardware budget. A lot of our sensors and CDs, a lot of these components are already purchased, so we have what these costs are, but mechanical costs and design costs, we don't know just yet. So we're included in next one, other expenses for the travel out of the competition, hotel, and travel and stuff like that. Kind of some of our ingredients, many of our critical components have arrived. We've completed the chat set and our future work includes fabricating working models, completing top models, and testing, always testing. Thank you so much for your time, everyone. Thank you. Questions? Okay, sorry.
So that's something that we haven't come across yet in this episode of testing thing. But so for testing design we're going to use, we're basically just going to hold it and actually kind of limit the force of gravity and assume the friction will be too great that it really spin. And then as for dropping it out, then we would do the size. I think that's just what we're using.
How would you use the second goal
Yeah, so that's something also that we're looking at. Like I said, now that the stack is sold, before we start reading up a whole lot. But basically, what we've been talking about is having kind of a ball bearing, so that we have a three ball that's going to be design figure of what's in place, and then something like a spring loaded hinge. Yeah, so once the force of the perspective, as soon as it's right. Yeah. It's something that we would definitely fully start about. Yeah. It's just that's what I would say.
So along those lines, sorry, are you guys sure that you're gonna have time to do enough testing? Is it like maybe have a doctor on the line after doctor and do a flight test that is actually probably
That's where I'm going That's why we do So that's why the structural areas testing so high. Then also the components that are actually going to break are probably going to be the components that that's hopefully when they drop it hopefully that we have multiple copies of all of them. So it's not just have one of them. And we wouldn't put the camera on as the testing. We wouldn't put everything.
Would you have any recommendations? Would you have any recommendations based on your listening stuff?
I mean, this is a calculation. So you know that in the case of 20% controlled failure, it's going to fall. Yeah, but you can calculate how the factors are falling. Basically, what kind of force is there.
So, right now we're still figuring out what we consider stable. And in the end, the code will have a way of, if it's getting too close to 300 meters, it'll just auto deploy. Stable doesn't really matter. But we'll probably look at the acceleration measurement and then see how, if it's falling straight down or if there's much wobble. Yeah.
It won't be looking like that.
Like the question is how to make the breadboard stable during flight, like in But during flight, we're going to be using the PCB, so that's going to be within 60% inside the go to the method on. So it's going to be like a vertical layer like this, and the PCB is going to fit inside, and the battery is going to be on the other side of the PCB. So that there should be enough. There should be enough protection in the mechanical design around it that the PCB doesn't just break.
So, see here, what's the plot area?
We're going to have a separate battery for this.
Other questions is like to the question on slide 26. So, the number of blades inside of the pool is 6. What's the rationale? And then under that you had your sub and order mechanisms. I'm more able to see fluid mechanism. I guess I was a little confused. Do you mean that would be like active powered mechanism or is it just racing in general? Okay. That may add in addition to the complexity to your mechanism. You can of having to store the blade or make sure that when it deploys doesn't snap off and then you make sure that they aren't like separate bits of code that you attach and processing things that are also flying all about. So you're gonna look into this in your test, obviously, but you're just gonna do code about which is passive slash which versus multiple mechanism.
We're still working on it.
Yeah, that was the one that was offered free to the people in the competition from the competition website. Team members. But yeah, you can get a copy if you're a team member on CanSat, you can download songs.
So speaking of software, you guys are using MATLAB for your ground station script. I guess I have a couple questions on that. One, your ground station MATLAB, what are those agencies that have MATLAB on it? I think you guys are using it. Yeah. So, exactly. Yeah. Know your life. To me, does MATLAB? Have you guys written your script already in communication? I don't know. MATLAB has libraries that handle like. Really? Okay. Interesting. I would like football.
Yeah, so pretty much the big problem is I'll just need to make sure that the ground station computer has a copy of that.
Okay.
Do you have a suggestion?
I would use Python, but that requires because it's not conventional one, right? So you have to pick up like another language, which isn't. Yeah, I'm sure Python like a lot. Fair enough. It comes down to personal preference on it. Really, I'm not gonna start a war there, so I'll let that go. Yeah, so then in that case, me and Brian have that license with you. So you guys using some foundation, so.
Well, yeah, we would be just using a student's copy, but if you want that included in the record, it doesn't have that added.
I'm talking about like
The ground station control computer, wanting a copy of that. No, that won't count. That shouldn't count to the $1,000 budget because it's a ground station.
Oh, sorry. Okay, then. That's my confusion. It's really good. And for your Mobius action cam, because it has a all of that, one of those little cam battery side. So I guess
We're not using it.
Yeah, we're taking that one out. And
separate now.
yeah, but it's still separate.
Yeah.
I wasn't close. Yeah, so we don't really have anything like that.
All data. Yeah, that's actually why we have. So one of the things is like we're gonna have kind of hopefully interviews from already once they're like grades. So that would be one way to reduce this grade. And we're also looking into like things that are on our report. That's gonna be something that's gonna be looking outside of the science about how good the job is.
Thank you all so much for coming and sitting through all that. Thank you.
And so we turn out for the GOT and CanSat slides like that.
I got a beautiful view of it. Oh yeah. There's one viewer, so thank you for viewing our nice little design review. Oh wow. In Google Hangouts, Avinash. How to go with?
Or if you yes, maybe I thought this one, so because they're gonna be live streaming. You literally like yeah, I mean, what you can do is like hold it and folks, we're going to be starting at Michigan time, so get ready for it. You can settle down, take a stretch, whatever you want, and then we'll start in 7 minutes. Oh, it's on Google Hangout. We have a bunch of like. They're all former. They're all former. So they can do their applause. Here, I just wanted to share it really on. That's second. Yeah, come on the site. Yes, I'll try yeah. No, I have one. I want to. So part of it just measured in because like it seems like everything's yeah, I mean I think we'll talk about that. Yeah, good call. Good boss.
All right. Get started. So welcome to Guardians of the Egg CanSat 2014 Preliminary Design Review. Here's an outline of our presentation. We'll start with the system overview, and we're going to go one by one through the design of each of our subsystems as we're working on so far. Finish off with integration and testing, mission operation, and finally requirements and compliance and units. Here's an overview of the team. I'm Colin Shum. Organization, so at the top, faculty advisor Brian Gilchrist, next time is Alan Trubala, team lead. Our team is broken up into subsystems. You'll see them present there. There's some acronyms you'll see in the presentation. And now systems overview. So, mission summary. Primary objectives are to deploy an auto-gyro descent mechanism, forward stable descent video, land our payload, the launch egg safely, transmit telemetry data in real time at 1 Hz. The bonus objective that we've selected is to measure the stability and angle of descent of the science vehicle in a accelerometer and store that data on board. One external objective that we've added is to make use of onboard GPS and buzzers so that we can easily retrieve the science vehicle after the end. There's just a breakdown of the system requirements. The big one is total mass, 600 grams plus or minus 10 grams, and what the rocket payload section. So here's a review of the system configuration. We decided to go with the stack configuration. This will allow for efficient integration of all our components in each section. It isolates all the electronics into one section of the science vehicle. The container for the form, the shell around the vehicle, parachute to the kind of part of the top of that section. And that's going to double to provide protection for the components during the ascent of the rocket. And the separation of the science vehicle from the container is going to be achieved by the servo-operated screw mechanism. So here's a rough CAD, just kind of outline the design. It's pretty cylindrical. The segments you'll see, we have the egg protection of the camera on the bottom, the electronics in the middle there, and the auto gyro at the top of the science vehicle, separation section, and then the parachute on top of the container. Here's a very early rough sketch that we did. We included this just to detail the separation mechanism a little bit more. You'll see the container attached here. It's really just a shell that goes over the science vehicle, and the screw is going to attach to the nut in the container, and that's going to be having a separate. So here is the system operations on the launch day. Pre-launch, it's going to be readying the CanSat, placing any removable components in there and securing them, the egg placed in, electronics powered on, and inserting the CanSat in the rocket payload section. Then we're going to go on to flight. It's on the later slide, and post-landing, the buzzer. The buzzer is going to activate an aero recovery as well as the onboard GPS data. So here's more detailed stages of flight. First, it's going to be ascending the rocket. So when the flight software is going to be initialized, the flight from the rocket into the attitude. Sensors at that point are going to begin collecting measurements and transmitting to the GCS. Stabilization after that, so the parachute deploys and slow the descent initially. once it's stabilized, assigned vehicles to detach from the container, and that's going to be initialized by the flight software when descent is slowed and the accelerometer reading suggests that it's pretty stable. At that point, the autogyro deploys, descent stabilizes, and the camera begins recording. Finally, it lands, the buzzer activates, and the sensors shut off. So here's a rough sketch, launch vehicle compatibility. Pretty straightforward. We're designing it to have plenty of tolerance with the rocket payload section. It doesn't get stuck, so that it deploys easily without any problems. All the external components, it's a cylindrical design, so for the most part, it's going to be a smooth deployment. The external components are all going to be placed in the exposed lower section, so they don't stick out horizontally. And some of those are the external temperature sensor, the wire antenna, and the cable. So I'm going to hand it over to Isaac with the sensor design.
We have chosen several sensors for our CanSat. One is GPS, altitude, temperature, accelerometer, and buzzer. For the MPK 339 is our selection for the GPS sensors, and the 10 UF IMU is our selection for the altitude, temperature, and accelerometer sensors. For our buzzer, we have chosen the small enclosed piezo buzzers. All sensors should be contained in the SP itself. And here is the requirements for the sensor subsystems. The most important one is actually the signed vehicle should transmit the telemetry data at 1 bit rate. Here is the GPS sensor, as I mentioned earlier. We actually chose the MTK 339 version 3. If you look closely, MTK 339 and the one bottom of it, it's similar, but for the version 3, it has breadboard adapters, so it will be easier to work with. That's why we chose the second one. And here is the altitude sensor trig selection. We have chosen the 10 UF IMU. The reason is because it has the altitude functions as well as temperature, so internal temperature sensors and accelerometer function. So it's actually better for budgets. So that's why we chose the sensors itself. For the buzzer, we have chosen the small enclosed piezo. The reason is because the oscillation rate is actually bigger than the buzzer 5 itself, so it could produce a louder sound. So it's easier for us to find our vehicle once it lands on the ground. And I'll pass to Evans.
Right, the goal of the descent control systems is to create a stabilized and slow descent of both the container vehicle and the science vehicle. For the container, we will be using a round parachute with a spill hole to achieve a stabilized descent of approximately 5 meters per second, with a separation at above 300 meters. The science vehicle will be using a three-blade autogyro system that will be able to fold in on itself to be able to fit within the container itself. This will also have a descent rate of 5 meters per second and immediate rotor deployment, and will be spinning separately from the body itself via ball bearings. Overall, this will have 150 gram mass. Here we have a visual overview of the process, starting at launch, near apogee deployment, and then parachute stabilization at above 500 meters. And our plan is to separate from the container vehicle at approximately 500 meters. From there, we'll have an immediate rotor deployment and then a autogyro descent. Here we have a CAD model of our autogyro, and in general, we're aiming for hinges really close to the base and about 30 centimeters more or less for the blade.
Okay, so for the percent control requirements, the first two are just basically the parachute and the auto gyro. But then the ones that are going to be more important coming soon with our prototypes and testing is going to be the descent control, auto gyro, and the parachute needs to withstand 50 pounds of shock. So, and then for the parachute control, we chose nylon for the material since it's available, it's in the lab. So that's why also we chose a color white for the area of the parachute, we calculated it to be approximately 100 meters squared. For the outer gyro, so I tried to for the materials that we used for that. And we chose plastic since it would be easy to work with, lightweight, and road length is going to be about 30 centimeters. This is just some of the math we did to calculate the approximate area of the parachute, and in our calculations, it was estimated that the descent rate would be about 5 meters per second, and the same for the outer gyro. And for the outer gyro, we're just going to keep prototyping until the desired descent rate.
I'm Cody Shuffles. I'm Dimitri. For the mechanical subsystem, our task was to design the structure for the CanSat. For this, we decided to use a wooden frame and plastic exterior body. The electronics will be stored at the top of the sensor located at the bottom. We already have the egg compartment, and that was for some of the components. And we have separate operation mechanism that's screwing up design, which it will also house the auto gyro sites. And over here we have some requirements that we have set earlier, the typing has to be 600 grams, plus or minus 10 grams. This is not FDA. The science unit must be included in the training specified either by 25 meters by 18. The rocket plane should not be used to sustain any parts of the CanSat, so as we go through, the scientific and development system, and the centrifugal system is 50 and sharp. The structure itself is 530 sharp. All the electronics are mounted on the structure. And we will also conduct drop tests and vibration tests on the computer to ensure that
So here we have a trade sim for egg protection. So we decided to just purchase our egg protection system from Apogee because they manufacture egg protection systems for competitions like this, so we know it's going to work and we know it's going to be efficient. And they actually have a lot of choices, but in the end, we ended up picking the horizontal tarp foam egg protector. It's 2.6 inches wide, which is the widest one they have. It's not super massive. And that allows us to not have to pad around it as much to keep it secure in our science vehicles. And it also provides egg protection on all sides, and it's been recommended by them to put a plastic tube around it. Put a plastic tube around it, and that helps distribute the force across the egg more equally and increase egg survivability. Here we have trade setting for our body. And there's a ton of materials that other teams over the years have used for CanSats. In the end, we ended up going with polyethylene plastic, which that's kind of it's the same stuff as tennis ball cubes and water bottles. So it's really easy to get, really easy to work with, and it's actually surprisingly strong for how cheap it is. And as an added benefit of the 2-liter soda bottles, it comes out to the approximate dimensions that our CanSat's allowed to be, which makes it really easy to prototype and move forward with.
So for our separation design, we have in our descent control compartment, we have a screw that runs between that and our container. It'll be powered by some of the motors and a servo. The servo runs for the continuous turns. But it will essentially, once we reach the target height, it will begin rotating and unscrews the screw from the nut, separating the container and the science vehicle. And in this picture, it's not shown very well, but there's one valve so it will rotate around itself. And here we have a mass budget, which we actually have masses for a lot of our components, which makes it really easy to figure out our total mass. We don't have everything yet, and a lot of them are rough estimates. But currently we're at 565.3 grams. That gives us a lot of wiggle room, and it's a lot easier to add mass than to take away mass, which puts us in a pretty good position right now. And give it to Colin for communications.
Next, this is the communication and data handling subsystem. Main tasks CDH subsystem are to receive data from the sensors at a rate of 1 hertz and transmit that data to the ground station computer in real time. It's also going to be recording the stable video cassette, storing that on an SD card on board. So some of the equipment that we've selected, a 900 megahertz XP Pro model is going to facilitate data transmission from the CanSat to the ground station. SparkFun OpenLog, which is going to save telemetry data to a micro SD card on board. Arduino Nano 3.0 and a Mobius Action Cam to record that video. So here's a list of the requirements. The main ones, as I stated, are to collect and deliver the various telemetry data and transmit that at 1 hertz. And XP radios are specified by the company. A few more of the requirements. A notable one here is if the video camera run at +9 rotate and the orientation more than 90 degrees. So here's a train study we did for the processor. We really compared two of the Arduino models, the Arduino Nano and the Arduino Uno, and found that really they have almost the exact same functionality. The main difference being the flash memory, which we aren't too concerned with, and the size we are concerned with. And for that reason, we selected the Arduino Nano. Like I said, same functionality, but significantly smaller and lighter. One con, and this really affects more just the testing of the design and the final product, but it's a little bit harder to integrate. You can't use the shield like with the Uno. Like I said, that just makes it easier to work with at this stage. For the real-time clock function, we're actually going to be utilizing 2 clocks, both in the software. On board, there's going to be a counter and a mid-flight software loop. That's going to double the mission time for the telemetry requirement. And on the ground, there's going to be a counter running in the ground station data display program. By comparing those, we're able to pose a reset tolerance if a significant discrepancy exists during the comparison, which is going to be going on at a regular interval. The flight software is going to be able to reset to the latest state of transmitted. That's to safeguard against if the Arduino turns off for a minute during the flight. The antenna selection, the real criteria, it's lightweight, that it doesn't take up significant space in our CanSat, and also it's able to reach from where the PCB is to outside the container so it can actually transmit the data. So for that, I selected a dipole wire antenna. So the simplicity of it allows us to design it to the desired dimensions. It's extremely lightweight, and it's going to be able to connect to the UFL connector on the XP Pro model we selected. For configuring the radios, they're going to operate a point-to-point system. The data is transmitted directly from the CanSat to the ground station that way. The net ID of the XP is going to be set for a T number, and for all the configuration, we're going to be using XCTU software. The main impact this has on the overall CanSat design. The way we configure it is going to impact the transmission power. It's going to require coordination with the electrical power system, and the transmission is going to be controlled by what the flight software state. The telemetry format itself, the telemetry data that we're going to be collecting and transmitting is air pressure, internal and external temperature, accelerometer data, that's our most objective, mission time, flight software state, battery voltage, and our team ID number. The data rate is going to be transmitting packets continuously at 1 hertz in an ASCII comma separated format saved to GCS computer and CSV file. Michelle with the electrical power system.
Okay, so I'm Michelle for electrical power. This is an overview of the components we're going to be using on the science table. We're going to have a nano controller, an XP radio with an explorer for integration of the circuit, the as a transceiver, open log to store the data, an IMU which has a triple function, a small sensor TMP36 for the outside temperature, a camera, and then GPS and a buzzer for location, and a transaction estimator set of things. Main requirements include battery that is well secured and cannot be used in a polymer. And also, we have to record battery voltage as you understand. This is an overview of the different block diagram. So we're going to have an external power switch, which is one of the requirements from the container as we go to the batteries, and which is going to provide 9 volts to the nano, and it has a voltage regulator, so it's going to either 3.3 or 5 volts for assemblies. We're going to have a voltage divider to measure battery voltage. We're also going to go, so the GPS, IMU, and TMP36 are going to collect data from the environment, and we just send it to the XP, which is the ground station, and we'll send it to the open log for memory. This is a case study for the battery. Selected the Duracell 9 volt because it has the best capacity at the voltage, and it has a snap connector as opposed to the other two, which have a flat terminal, which requires another component. This is the power budget, which I calculate the power consumption capacity that each component will drain. And these are estimated numbers. We still have to do a CanSat and do a lot of testing to make sure the power is supplied. And the camera's not included because it has a separate battery and charger. This is how we will measure battery voltage. We're going to use an iterate pin on Arduino because it measures into voltage more accurately than the analog pin. However, it only operates to 0 volts with resistors to reduce voltage, and they must be of high value in order to keep the current flow, not drain the battery more. So the battery will connect to the first resistor, then to the iterate pin on Arduino, then to another resistor of value, and then to ground. And then using that equation, we will determine the battery voltage. And now it's like software that
complex offer. So basically what we're going to be doing is we're going to be taking data from the sensors and then deciding when to store and transmit them based on certain conditions. We will be doing this using the C++ programming language and the Arduino IDE. And basically what we've done so far is we've published the first version of what our actual code is going to be, and we've managed to get meaningful data from a pressure sensor.
So this is our main flight software architecture. It's mainly in 2 parts, pre-deployment and post-deployment loops. When the system first turns on, they'll try to determine whether science people is deployed. It's part of our reset action plan, we'll explain later. And after determining whether it's deployed, we'll go into the respective loops. The pre-deployment loop will just be measuring sensor data, random flight state, and transmitting, and continuously checking whether the correct altitude and the correct flight state have been reached. If that does occur, it will deploy the science vehicle and go into the post-deployment loop. Post-deployment loop is similar to pre-deployment loop, except it checks whether the CanSat has landed, and once it has determined that the CanSat has landed, it will go into continuous buzzer sounding and transmitting of the GPS location.
These are the requirements that we have for flight software, the 2 biggest of which are we have to gather data from the various sensors and And we have to maintain flight states based on what our sensors are telling us.
Our flight software recovery plan is mainly based on altitude, accelerometer data, which is and also the deployment indicator. We're going to be storing our telemetry and our whether the scientific was deployed on SD card. And these are criteria for flight state. Our software development plan is to produce code early and test early. As Sam mentioned, we've already developed a prototype of our actual flight software with the sensors we already have in-house. And we're going to design code so that when the parts do come in, we only need to be comfortable with 2 lines of code. In future work, we're closely with EPS, SMS, investigation, and work together. And also focus on the core, which we've identified as data storage and transmission, mainly because they're the most complex and the most important in my opinion. We're adding more sensors collection and complexity. And now I'm going to talk about the actual system.
Thank you, David. So my main task as a ground control station is responsible for the telemetry reception, as long as developing the antenna design and as well as the layout. Some of the equipment that I've been working with so far and will continue to work with is the laptop computer, an antenna that we'll be receiving, the XP Pro that Colin talked about earlier, along with the XP. So a couple of requirements for the ground control station is each team will have their own portable ground control station in which data will be sent from the CanSat science vehicle. It will be plotted in real time in scientific engineering. We have yet to pick a antenna yet. However, we have narrowed it down to the Yankee Doodle and the parabolic dish. As you can see, they have pretty similar game patterns. However, with the parabolic dish, it's a little bit more narrow and goes a little bit farther out from the antenna itself. You can see that the game pattern, or the game itself, is a little bit higher for the parabolic dish, as long as our friends over at Astra have saved you a phone on the current antenna that we have in-house. So there really is no, I guess, preference between the two of them when it comes to our money. However, obviously, you have 2 different costs. I believe both of them are around $50 to $80. So we're doing a couple more calculations based on if we could choose a parabolic dish, that would be nice to give us a little bit more range. However, because it is more narrow, we would have to work on making sure that we change the angle as the scientific vehicle falls to make sure that we keep so for the CanSat integration and test. So each one of us obviously has some tests to perform as we go forward. With the container and the scientific vehicle, we have to make sure that all the electronics are contained within the scientific vehicle. Obviously, we have to make sure that that all works, and that's been done by the flight software team. The electronic subsystem, including the flight software team, the sensors, and the communication data handler. They've been working closely at all times to make sure that they have a good chemistry of making sure that all of the electronic devices are working. The descent control vehicle, obviously, working with making sure that they have enough space allotted within the device itself in order to make sure that the wings flap up. The mechanical team, making sure that we do not break our egg. Working on some stuff with that. Another for the descent control, making sure that the auto gyro prototypes tested are the approximate CanSat weight. And finally, the electronics, having a global program tested upon having all the additional sensors that we'll have the communications, including myself and ground control station, making sure we have a range test, making sure, like I said, we have a calculation for the test to make sure that we can pick up the data from so far away. Also plotting the software online, working with either MATLAB or Python. And then finally, the system of high altitude drop to test plan once the working prototype is successfully. And then finally, I'll be doing the mission and operations analysis. Colin mentioned a couple of these earlier, but just to go into a little bit more detail, after you arrive in the great state of Texas, we'll set up the ground station and assemble the antenna. Make sure that all the communication devices are working and that we have last minute assembly with the CanSat. Moving on to pre-launch checks, obviously we have to make sure that all the subsystems are working properly and the antenna is positioned correctly. The ground station is operational. And then obviously estimate our landing zone. And then integration into the rocket, we have to make sure that the egg is in the lander. That would kind of be a problem. Turning CanSat on, obviously very important. And then for the rocket launch, once the launch begins, we'll make sure that the ground communication with the CanSat is operational and start receiving that data. The deployment of the parachute as the CanSat scientific vehicle drops out, we'll make sure that the data is being provided by the software. The separation and having the auto gyro deployed, and the landing as the buzzer starts and finally, as we recover, make sure that everything is all intact, and make sure that we are able to analyze all the data that we have received, as well as the telemetric data we could carry out and analyze. In the post-flight check, just make sure that we analyze all of our data and put it together in a presentation that will be given. So our recovery method, as Isaac mentioned earlier, includes the speaker along with the GPS that we are hoping to integrate with that system. And hopefully that will allow us to find thank you.
Alright, we're going to wrap it up with just a quick check on the requirements and compliance so far. So the current compliance of our overall system, all component restrictions have been met, so any component we've selected does meet the company guidelines. We're under the mass budget and the cost budget pretty thoroughly so far, and all the work that we've completed has the requirements. Pretty much any requirement following slides is marked no comply is only that way because it's still a work in progress. It doesn't mean they're finished yet, but any of those problems will be remedied no later than we have our prototype. It shouldn't be a huge issue. Here's just an overview of them. I'm not going to go through all these. And then finally, we have just our system cost budget. Most of this stuff is a pretty accurate cost. Pretty much anything with a decimal is the actual cost. The only estimate ones have to do with the parachute material, structural material, and that's just going to come down to how much we end up using for our final system. But as you'll see, we're well under the total budget of $1,000. We don't anticipate that being a problem whatsoever. But if we do start getting closer to checkpoints. So in conclusion, major accomplishments of our team so far. Components have all been selected and acquired. We have started prototyping drop tests with the auto gyro blades, starting to work with the electronics, developed, as Sam mentioned, the retrieving data, starting to transmit that. Finally, upcoming milestones. We want to complete the flight software program, integrate that into a flat sat, test that functionality, manufacture actual set mechanisms with the materials that we plan on using, and finally get data transmitted from the flight software to the ground station distance, test the functionality of the XP radios and antennas. Thanks for coming out.
In general, most auto gyros use 3 propellers, and in addition to that, it helps reduce the amount of weight, and from our testing, it should be sufficient enough to provide enough lift to slow it. We'll be making up.
Oh, the CAD drawing is mostly to get an overall mass budget of the system, because right now we're working with easier materials to work with, such as wood and foam board, but later on we'll be using plastic. And in addition to that, that was a way for us to see how much different materials would weigh in.
You mean like buying an entire auto? I guess we haven't considered it. The major worry there would be the blades. I don't know if you buy it, but it's have that functionality. That's what they're
Related topic, how are you planning on using it? It sounds like it's on wireless.
In general, for the images, we still need to work on that. We're going to be working with MEC to figure out how that will integrate with the overall system. So far, we've been using designs that have a more flexible blade to see how it will open up just based purely on the air catching the blades. So far, that is working, and from there, we'll have to talk to MEC about actually integrating in just as that.
It's just to reiterate to both the teams. This is a big lesson learned from previous years of CanSat. You'll definitely want to use spring hinges unless it does make sense in this application, but definitely for like your auto gyros, you want to use spring hinges because you can't be guaranteed that the substream is going to be perfect and pull your auto gyro wings out. So yeah, definitely use some torsion springs on there.
The way that an auto gyro works, it is purely powered by the wing catching the blades itself. So the wind will power the blades, and because of the ball bearing that is attached to the blades, it should spin independently of the wings.
All that does is turn the screw to separate. It doesn't have anything to do with the auto gyro inside of the asset. Servos, you would something about how the non-arcade actually works. Full resolution like that.
Yeah, so most RC servos are going to be like give it a PWM signal
Yeah, so they're continuous servos which rotate continuously, and most of your servos that you buy at the hobby stores for airplanes, they only have like plus or minus 180 degrees. So yeah, you want to look at the actual servo. You can hack a non-continuous servo to make it continuous, but yeah, it's up to you.
Usually it was they tried to do an mouse budget, but now that we actually have one, we're so far under, it's not a consideration.
We're working with that. Yeah. We weren't able to do it by the time. For the next one, that's definitely one of
on the power source plate study for on slides 60, the camera was included in the power budget because it's chargeable by USB. But the battery that's going to be on board, if you're sticking with the Mobius and whatever, and that you can.
We just got confirmation.
Okay.
But in that case, we would have a separate battery that would make it or
if you're gonna stick with this camera choice, I would not be in the separate battery.
Yeah, and I was talking to Mark, maybe? So many emails. But yeah, basically, my rationale for having a separate battery for your camera system and the rest of your avionics that are flight critical, well, because they're flight critical. If your camera, develops a short circuit or something, your harness fails, then yeah, you don't want that to be your point of failure.
So far we're just mostly focusing on just making basic prototypes. Later on, we'll go into the lab and actually manufacture these ourselves. How plastic will be working with that to actually figure out how to put it out in place.
Our main focus is you guys potential concept.
Thanks a lot for coming out. Really appreciate it.
All right, thanks everyone. If you haven't signed in your laptop on the back, if you do that, that'd be great. I probably can sign up your laptop.